Good morning, students. Myself, Dr. Prema T. Akkasaligar, working as professor and PG coordinator in the Department of Computer Science, BLD Engineering College, Vijaypur. Next type of CPU scheduling is known as round robin, RR robin. It is designed basically for a time sharing system. Here, a small unit of time called time quantum or time slice is defined. A time quantum is generally from 10 millisecond to 100 millisecond in length. The ready queue is treated as a circular queue. The CPU scheduler goes around the ready queue, allocating the CPU to each process for a time interval of up to one time quantum. The CPU scheduler picks the first process from the ready queue, sets the timer to interrupt after one time quantum, and dispatches the process. There are the two things happen while in round robin technique. First thing is, a process may have a CPU burst of less than one time quantum. Here, process itself will release the CPU voluntarily. The scheduler will then proceed to the next process in the ready queue. The second thing may happen is, the CPU burst of currently running process is longer than one time quantum. The timer will go off and will cause an interrupt to the operating system. A context switch will be executed and then process will be put at the tail of the ready queue. The CPU scheduler will then select the next process in the ready queue. So, each process must wait for no longer than n-1 into q time units until its next time quantum. If the time quantum is extremely large, then round robin policy follows first come first serve scheduling. If time quantum is small, it acts as a processor sharing. We can say that round robin technique is a preemptive version because no process is allocated to CPU for more than one time quantum in a row. If a processor's CPU burst exceeds one time quantum, it is preempted and put back into the ready queue. That we can see with one example shown in slide number 12. There are three processes P1, P2, P3 with a burst time of 24 millisecond, 3 millisecond and 3 millisecond respectively. The time quantum is 4 millisecond. So, as P1 has arrived first, CPU is allocated to P1 but for a quantum period of 4 millisecond. After that, it switches to P2 for 3 millisecond. Then it switches to P3 with 3 millisecond. Then the next CPU burst cycle of P1 is 20 millisecond. So, for every 4 quantum time, the CPU is allocated to P1 and it is shown in the Gantt chart. So the Gantt chart completes up to 30 milliseconds. So we can say that higher average turnaround time is found in round robin technique compared with shortest job first. So Q should be large compared to the context switch time. So Q normally we said it is between 10 millisecond to 100 millisecond if the context switch time is less than 10 microsecond. This figure shows the effect of context switching on the performance of round robin scheduling algorithm. Here we assume an example that have only one process of 10 time units. If quantum is 12 time units, the process finishes in less than one time quantum with no overhead. If the quantum is 6 time units, however, the process requires 2 quanta, resulting in a context switch. If the time quantum is 1 time unit, then 9 context switch will occur, slowing the execution of the process as shown in the figure. This figure shows turnaround time varies with the time quanta. That is, turnaround time is also depends on the size of the time context. As we can see from the figure, the average turnaround time of a set of processes does not necessarily improve as the time quantum size increases. So in general, if the context switch time is added, the average turnaround time increases even for smaller time quanta as more context switch is required. The figure shows the example for multi-level queue scheduling, where we have the lowest priority given to the student processes, next batch process, next interactive editing process, interactive process, and highest priority is given to the system processes. Next type of CPU scheduling is known as round robin, RR robin. It is designed basically for a time sharing system. Here, a small unit of time called time quantum or time slice is defined. A time quantum is generally from 10 millisecond to 100 millisecond in length. The ready queue is treated as a circular queue. The CPU scheduler goes around the ready queue, allocating the CPU to each process for a time interval of up to one time quantum. The CPU scheduler picks the first process from the ready queue, sets the timer to interrupt after one time quantum, and dispatches the process. There are the two things happen while in round robin technique. First thing is, a process may have a CPU burst of less than one time quantum. Here, process itself will release the CPU voluntarily. The figure shows an example of multi-level feedback queue. So we see that the feedback of first queue is considered for next level, then feedback of second queue is considered for the next level. Next scheduling algorithm is multiple processor scheduling. With the single processor scheduling, there is no single best solution found. So multiple CPUs using load sharing is discussed here. But scheduling algorithm is more complex. Many processors with homogeneous in terms of functionality are considered here. There are two approaches to multiple processor scheduling. First one is asymmetric multiprocessing, where all scheduling decisions, IO processing, and other system activities handled by a single processor. It is simple because only one processor accesses the system data structure, reducing the data sharing. The second approach is symmetric multiprocessing, which is known as SMP. Here, each processor is self-scheduling. All processes may be in a common ready queue, or each processor may have its own private queue of ready processes. Here, scheduler must be programmed carefully to handle data sharing. All modern operating systems support symmetric multiprocessing in case of multiple processor scheduling. Processor affinity. A process has an affinity for a processor on which it is currently running. That is, when a process migrates to another processor, the contents of cache memory must be invalidated for the first processor, and the cache for second processor must be repopulated. Because of high cost of invalidating, SMP tries to avoid migration. There are two types of affinity exist: soft affinity and hard affinity. Soft affinity is possible for a process to migrate between processors, where hard affinity process will not migrate to other processes. Variations including processor states are possible here. Next we'll discuss about load balancing. Load balancing attempts to keep the workload evenly distributed across all processors in an SMP systems. It is used in system having each processor with a private queue of eligible processors to execute. A processor with common run queue load balancing is not necessary. There are two types of load balancing. One is using push migration and another is using pull migration. In a push migration, a specific task periodically checks the load on each processor, and if it finds an imbalance, it evenly distributes the load by pushing or moving processors from overloaded to idle or less busy processors. In a pull migration, idle processor pulls the waiting task from busy processor. Now we'll discuss about thread scheduling. We explore the scheduling issues involving user level and kernel level threads here and offer a specific example of scheduling. So when p threads are supported, the threads are scheduled and not the processors. The distinction between user level and kernel level thread lies in how they are scheduled on systems implementing the many to one and many to many models. The thread library schedules user level threads to run on an available lightweight process known as process contention scope. In short, we call it as PCS. When operating system schedules kernel thread onto physical CPU, to decide which kernel thread to schedule on to the CPU, the kernel uses system contention scope, which is also known as SCS. So dear students, in this slide I have given the video play link of different scheduling algorithms like SJF non-preemptive, SJF preemptive, round robin scheduling and priority scheduling, so that the examples are more clear for you. You can go through these examples and try to solve the examples which are given in assignment 7. Thank you for patient listening. Thank you all.